So we see problem 7.4 on the screen now. Let's have a look at the problem first. We are given a figure which shows the physical system. We basically have a pendulum on a rod system where the rod can be actuated by a force or a torque U, and the different state variables are the psi and the theta, the angles made by the rod and the pendulum with the vertical direction, and their derivatives. So the differential equations governing this physical system are given here. We are asked to design a controller using spectral factorization and the root-locus technique. We will shortly see how we could combine ideas from these two seemingly not related concepts to design optimal controllers. The control constraint given to us, or the design constraint given to us, is that the time constant should be 1/3. And eventually we are asked to simulate the system responses for a given initial condition, which is given here. So now let's start with the first part, which asks us to derive a state space model for the given system. So let's first write down the differential equations in a familiar format, which is psi double dot is equal to minus 3/2 psi, plus 3/2 psi plus theta plus u, and theta double dot is equal to minus psi double dot, which is nothing but minus 3/2 psi minus theta minus u, and then we have minus theta additionally here. So now we're given the state vector x as psi dot, theta dot. So x dot is psi dot, psi double dot, theta dot, and theta double dot. Now we can write these as follows. So psi dot is directly the state x2, so we'll write x2 here. Psi double dot is given by this expression. So we have 3/2 psi plus psi, that is 2.5 psi, which is the first state. So we have 2.5 x1. Then we have theta, which is the third state. So we have plus x3. And then we have a control input u, so which I write it as it is for now. Theta dot is just the fourth state, and theta double dot is now again minus 3/2 psi minus psi, that is minus 2.5 psi, and psi is the first state, so minus 2.5 x1. Then we have minus theta, which is the third state, and we have another minus theta here, so we have minus 2 theta, so we have minus 2 x3, and then we have finally a minus u, which I write as it is again. So this now can be easily written as 0, 1, 0, 0, because we have the second state. We have then 2.5 times the first state, 1 times the third state. We have only the fourth state in theta dot, and we have minus 2.5 times x1, no x2 term, minus 2 times x3, and no x4 term, times x1, x2, x3, and x4. And then we have a u term which we've not accounted for yet, with a positive sign in the second equation and a negative sign in the fourth equation. So we have an A matrix and a B matrix, and we can now write down the system in the form of the state space model as here. So that's the first problem. Now that's the first subproblem, the A part. Now once we have that, we are supposed to design an optimal controller with a time constant over 1/3. Now, this is a design constraint, and for first order systems, this just means that the closed loop pole, uh, is at -3, or the real part of the closed loop pole is at -3. But we can sort of generalize this for higher order systems, and we can say that this roughly corresponds to the slowest pole being at -3. So our design constraint is basically that all poles, or the real part of all poles, should be less than or equal to -3. So how do we do that? One way could be to basically just guess the pole locations. So now here we have a fourth order system, and we can try designing for different pole locations for these 4 different poles. That's not an easy task. We're not sure how to place these poles. So in order to make the tuning easier, we use this idea of combining spectral factorization and the root-locus technique. So let's quickly recap what we learned in the spectral factorization theorem. At this point, I'd like to recommend that you have a look at exercises 5.1 and 7.2, where we dealt with spectral factorization before. So let's quickly review the spectral factorization result. If we have the following optimal control problem, let's consider the scalar case, or the single input single output case. So we have this cost that we want to minimize, subject to the system dynamics and the initial conditions. So what we know is that the closed loop optimal poles are the eigenvalues of the Hamiltonian matrix, and we know that the eigenvalues of the Hamiltonian matrix are equal to the poles of the closed loop shown below. And this is the block diagram. Note that because we are considering single input, single output systems, I will omit the transpose, and R inverse is just 1 over rho. So that is the spectral factorization theorem. And what we did further is that we know that the closed loop poles of this block diagram, of this closed loop, are given by the characteristic polynomial of the roots of the equation 1 plus p of s over a of s times p of minus s over a of minus s times rho equal to 0. Now, at this point, we can draw ideas from the root-locus techniques, wherein we can define this as our L of s and this as k. So now we have a block diagram with a k and an L of s in open loop, and we wish to plot the closed loop poles for varying values of k. And This can be done by using the root-locus method, the root-locus technique. So if you are unfamiliar with the root-locus technique, I encourage you to have a look at the lecture notes on Introduction to Control Systems, so the course that we offer before the Control Systems Theory and Design course, or the first course that we offer here, or you can just read about it in some good control book. So the basic idea is that we plot in the complex plane the closed loop poles of this block diagram. And the tool that you will use for this one is called the RL tool in MATLAB. So for our problem now, what we have is A and B. Now we want to regulate the output theta plus psi, and therefore we can choose C to be equal to 1 0 1 0. That will exactly pick up theta plus psi as the output. So once we do that, we have the transfer function g of s as c times si minus a inverse b, and then we can define L of s as g of s times g of minus s. Once we have L of s, we can use the root-locus tool to plot the closed loop optimal poles for our problem. So in this picture, you see the plot of the root-locus tool for different values of k, which is on our row. You see the different pole locations along these curves. Note that we have symmetric poles. And that is because we're plotting the poles of the Hamiltonian, which are symmetric about both axes. So what we know is that the stable poles, that is the poles on this side of the complex plane, are the optimal closed loop pole locations for a particular value of rho. So for example, if we now choose a particular value of k, we get the closed loop pole locations at these points. And now we can select the value of k such that all poles are to the left of the point -3, which is somewhere here, which is what is shown in the denoted by the pink squares. So we can choose a value of k such that all pole locations now, which are 1, 2, so shown by the circles, are to the left of the point -3, 0 here. So we should however note that the value of rho for which these are the optimal closed loop pole locations are the inverse of k in the root-locus tool. Now once we have these pole locations, we can simply use the place command to find state feedback gain f that places these poles at these locations. So once we do that, we're done with part B, and in part C, we're just required to plot the system response for the initial condition given as this. So this figure shows the response. For this initial condition, note that this is output y, which is theta plus psi, which is 2 because of our initial condition. And we see that this output is regulated to 0. And that's it for this problem. Thanks a lot.